Okay, so this is the one test. We'll go through this real quick. Particles are shot into a region that contains a uniform electric field. Keyword electric. Don't miss that term. Don't think about magnetic fields, or you'll get things messed up. Okay, so the numbered line shows the path taken by 5 particles. A negatively charged particle with charge negative 3q follows path 2. So this is negative 3q while it moves through the field. Do not consider any effects to gravity. So, number 1, in which direction does the electric field point? Draw it on the picture. And why does it point in that direction? Well, if a negative charge goes up, then that means the field must point downward, because remember, fields point from areas of positive charge to negative charge. So if the negative charge is going upward, it's going towards the positive area. So the field is down, because charge moves in opposite direction of field. Okay, which path would be followed by a helium atom, an electrically neutral particle, and why? Well, I think that's pretty obvious. This is helium 3. No charge, no force, no direction, deflection. What path would be followed by a charge of positive 6q? Well, that would have to be 5, path 5. I'm not going to write down the explanation because I'm just going to tell it to you. The positive particle will move in the opposite direction of the negative 3q charge, so that would give you options either 4 or 5, but the magnitude is higher. The magnitude of the charge is larger. It's double, in fact. So that means it's not going to be 4. 4 would be positive 3q, so it has to be larger. The only other option is 5 plus 6q. Okay, so you've got the field from these 4 charges, and it says what is the net field at point P? All right, so you've got 4 different point charges. The electric field points away from a positive charge and towards a negative charge. So basically what you have, these two cancel each other out. So you could say, let's first number these. 1, 2, 3, 4. E1, E3, I'll put it right here. E4 and E2. Well, these have the same magnitude. So E1 plus E4 equals 0 because they oppose each other. So they cancel out. So that means the total field, I'll just call that E, equals the magnitude of E1 plus E2 plus the magnitude of E4, because they're both in the same direction. If I were to look just at point P, you would see E1, E3, E4, and E2. Something like that. Okay, so what is the electric field? Well, that's just K, Q2, R2, plus K Q3 R3, where R2 and R4 is as such. Oh gosh, these subscripts all mixed up. This is R4. Okay, well we know that R2 equals R4, so we can dispatch with that stuff quickly. So K over R is equal to Q2 plus Q3. So far so good. We just need to find out what the radius is. If we have then, let's call this capital D equals 2 meters. So we can say D, and then we know the other side is D. This is the hypotenuse, so this would be, excuse me, this is R, and this whole thing would be 2R. So R. Okay, so 2R squared then is equal to D squared plus D squared, which is equal to 2D squared. 4R squared is equal to 2D squared. Or 2R squared is equal to D squared. So R squared is equal to D squared over 2, and R is just equal to D over square root of 2. Well, I shouldn't have boxed that, but that goes in here. E then is equal to K times the reciprocal of the, well, I'll just write in the numerator. D over square root of 2 times the absolute value of Q2 plus the absolute value of Q3. And you can plug in the numbers and solve that for yourself. Alright, so let's look at the equipotential lines here. How much work is required to move a negative 1 microcoulomb charge from B to C to D? So that's B to D to C. So first there and then there. Well, work is always equal to negative change in potential energy. In this case, it equals negative change in electric potential energy, which then we know the electric potential energy is equal to negative Q delta V, but delta V equals 0 because we go from, I guess that's 10 volts to negative 10 volts back to 10 volts. So delta V equals 0, therefore work equals 0. A positive point charge is placed at F. When released, describe what happens. A diagram may be helpful. Okay, so when released, a positive point charge is always going to move towards the area of less positive potential. Or we could say that more negative. So, and it's going to be perpendicular to equipotential line. So F moves toward H. What is the magnitude of the electric field at point A? Well, the electric field, you know, is equal to negative change in voltage over change in distance. So at point A, we go from, let's say, positive 40 volts to positive 20 volts. So that's a 20 volt difference over negative 20 volts. Okay, over delta S, which is, well, we're going in the negative direction, so negative 0.2 meters. Sorry, let's make sure I get the signs right. So this is equal to V final minus V initial, S final minus S initial, so it's equal to negative V final, which if I'm going, I'm just taking 2 points on either side, so I'm going from here to here. So that is plus 20 volts to plus 40 volts plus 20. So this is 20 volts minus initial, which is 40 volts. And in this case, this is final is 0.2 meters minus initial, which is 0.4 meters. Okay, so this is negative times negative 20 volts over negative 0.2 meters equals, okay, so that's negative 100 volts per meter. And the negative sign, you could just solve for absolute value and then say you know the electric field is going in this direction because it's going from higher voltage to lower voltage. That would work as well. Are moving directly toward one another when they are very far apart. Their initial speeds are 3 times 10 to the 6 meters per second. What's the distance of closest approach? Okay, so V1 naught equals V2 naught, which equals 3 times 10 to the 6 meters per second. V1 final equals V2 final equals 0. Okay, and they're all mass of protons. You can look that up. So this is a very simple application of the conservation of energy. Energy in the beginning equals energy in the end. In the beginning, it's kinetic energy plus potential energy equals KE final plus PE final. We know in the beginning potential energy is 0 because it says they are very far apart. So electrostatic potential would be the only potential you could have. That's 0 because they're very far apart. In the end, kinetic energy is 0 because they're not moving. So the kinetic energy in the beginning equals KE1 naught plus KE2 naught, and that equals the electric potential energy. In the beginning, the kinetic energy is 1/2 m, which is mass of a proton, v squared, and this is all going to be multiplied by 2 because the kinetic energy of each particle is the same because they're moving at the same speed. Now the electric potential energy is defined as charge times the potential difference. In this case, we'll think Q1. We'll look at the, let's say we have 1 and 2. So I'll look at the charge 1 and the potential from charge 2. So that's defined as Q1, and then the potential difference of the second charge is K Q2 over R. So this is the potential difference in bringing charge 2 in from infinity out to this position in relation to charge 1. Alright, let's see. So this would be 2 times 1/2, those would cancel. So it's MP V squared equals Q1 Q2 K over R, which just equals E squared because each proton has the elemental charge, right? Times K over R. Then R is equal to K E squared over mass of a proton times V squared. You can plug in the numbers there. Okay, using the following circuit, first of all, let's find the equivalent resistance between points A and points B. So that means we're going to have to combine 2 and 3 first, and then combine our 2 and 3. So R2, 3, I should have drawn the circuit, okay. So I've taken this and reduced it to this, where this is R1 and this is R2, 3. That is the 1 over R2 plus 1 over R3 reciprocal, because these two are in parallel, so we're combining those two. Alright, so if you put in the numbers, let's go ahead and do that for you. You've got the answer, so you can do that. R23 equals 20 ohms. So now, what is the equivalent resistance between points A and B? We still have to combine R1 and R23. So then we have R123. R123 is just simply R1 plus R23, just 10 ohms plus 20 ohms equals 30 ohms. So that is the equivalent resistance between points A and B. What is the potential drop across the 10 ohm resistor? Well, I need to find the current through the whole circuit. V equals IR, where this is R123. Okay, we know the potential, we know the resistance, we just need to find the current. So that equals V over R123. This is 30 volts over 30, what was it, 30 ohms? 30 ohms, yeah. So that equals 1 amp. So that's the resistance through. Now, we want to find the potential drop across the 10 ohm resistor. Okay, so we know 1 amp is running through that. So the voltage drop equals IR equals 1 amp times 10 ohms equals 10 volt potential drop. What's the potential drop across the 30 ohm resistor? Well, that's much more complicated, because we know there's a potential drop here, and we know the potential drops across the whole thing, but the potential drop across this resistor is the same as the potential drop across this resistor. So the current comes in and splits, so the currents are going to be different, but the potential drops are going to be the same. So, in essence, what we need to do is find the potential drop across R23. V23 is equal to I23 R23, and the current is still the same. The current through R1 is the same as the current through R23. So 1 amp times R23, which is 20 ohms. The voltage drop is 20 volts, and we know the voltage drop across 3 is equal to V23, which equals 20 volts. And that's the last question for the Unit 1 test.